Another type of calorimeter is a bomb calorimeter. With these types of calorimeters, the heat capacity of the calorimeter will be used in our calculations. We're going to use some equations that we've already seen in slightly different ways. We'll use a rearrangement of the heat capacity equation. Remember, heat capacity is Q over delta T. So we can rearrange that to solve for Q and come out with Q equals heat capacity, capital C, times delta T. When we use this equation, we will use it with all the variables related to the calorimeter. Unlike traditional calorimeters, which typically have water as the surroundings and the calorimeter itself is assumed to neither absorb or release heat, with bomb calorimeters, we're going to assume that the surroundings are made up of both water and the calorimeter itself. Since Q of the system equals negative of the Q of the surroundings, Q of the sample equals negative of the combined heats of the water and the calorimeter. In this example, we have 3.12 grams of glucose being burned in a bomb calorimeter. The temperature of the calorimeter increases from 23.8 degrees Celsius to 35.6 degrees Celsius. The calorimeter contains 775 grams of water, and the bomb itself, that is the calorimeter, has a heat capacity of 893 joules per degree Celsius. We're trying to solve for how much heat is produced by the combustion of the glucose sample. First of all, we're going to do a calculation based on the calorimeter itself, using the heat capacity of the calorimeter. We can plug in the heat capacity, capital C, which is 893 joules per Celsius. Then we plug in change in temperature for our calorimeter, which again is final minus initial. So that will be 35.6 minus the 23.8 that it started out as. We come out with 10,537 joules as the Q for the calorimeter. The Q for the water is calculated using Q equals mc delta T. Mass of the water is 775 grams. The specific heat of water is 4.184. The temperatures of the water are the same temperatures as the calorimeter. We do 35.6 minus 23.8 for the water, as well as for the calorimeter. For the water, we end up with a heat of 38,263 joules. We can add up the heats for the calorimeter and the water. Then the opposite sign of that will give us the Q of the sample. We have negative of 38,263 plus 10,537, which gives us negative 48,800 joules as the Q of the sample. We can put that in kilojoules to give us a more manageable number of negative 48.8 kilojoules. That negative sign is telling us that heat is being released. It's going out of the sample. When you look on the back of a box of macaroni and cheese or cereal, you see those big C calories listed. The way those are found is by using a bomb calorimeter. The sample has to be prepared. It's going to be weighed, mixed in a blender, freeze-dried, ground into powder, and formed into a pellet. And then once it's prepared, it's put into a bomb calorimeter and burned. The heat that is released from that process of burning it can be calculated in a way similar to the previous problem, and joules can be converted to calories to give the number on the back of the box.